Hey, this is a project demonstration of a XML parser that I've been working on for the last few weeks. So this project takes XML and converts it into an AST structure, first of all tokenizes it, parses it, and returns an AST, an abstract syntax tree. It also has some semantic analysis to make sure that if you input what looks like valid XML but is semantically wrong, we can catch that out. And I also built a translator to JSON, which would be where this project would be most useful in the future. So let's start. On the right here, I have the input XML, something simple to start off. And when I run the program, it's gonna tokenize the XML, and it's gonna output the AST representation, and it's also gonna output the JSON. So if I run this right now, here we can see the AST representation that's been prettified. So you can see it starts off with a tag, which is this hello thing, with an open tag, it says hello. It has some content, and the content itself is another tag, which is this world. It has world, and then has another context. So this is done using recursive descent, so you'll see a lot of this write recursion type pattern in here. But you can see, for example, this world tag, which has 1, 2, 3 in it. Here we see the data of that tag there. 5, 4, 3 down here, which is the second one. If we have a look at the other one, at world, the third world, it has an attribute, which is this is a string. And you can see we have a tag name, and it has an attribute that is this is a string as well. And then this obviously you can have as many attributes as you want. You can have as many tags as you want because of the write recursion. So yeah, this just works. And obviously you can have these nested structures, like you have the tag something, which inside of it has another tag, and all the way to the end with some the close tag on something, and then finally the close tag on hello, which is the very first one. If we move on to the second part of this project, which is the conversion into JSON, this is a lot easier to look at. So we have a JSON that contains hello, inside of it its own JSON object containing all this stuff on the right, has world, and notice this is actually an array, because the program is clever enough to understand that you have 3 tags with the same name, and in JSON you represent that as an array. One design decision I made is that the attributes in XML are lost. They are not implemented into your JSON. So that is a potential problem, and maybe one that I could fix. Next up, we have the key something, which is the something tag, inside of it having world again with the tags. So yeah, that all works quite well. I have another example to show you, which is not going to be much of a looker, to be honest, because it's really big. And there it is. But if I run this on the different input text, you can see everything works just the same. A lot of AST syntax and stuff. This is all very hard to read. We can start off by just having a look at tests, and it contains it keeps going down. This test tag, yeah, it's not very nice. But the JSON is a little bit easier to look at. So we have test, inside of it an array that contains some JSON and some more JSON. So you notice that I'm able to pass not just arrays of data, but also arrays of JSON, just like that. And that's sort of it for what it can do. Just to demonstrate the syntax, the semantic analysis, I'm going to go back to that simpler example that we saw before. So this one here, make sure it is running on that. Yeah. If I kind of break this a little bit, so let's say I remove this tag here on the world, and run. First of all, this will give me a parsing error. This will actually panic, but it's an error nonetheless. Okay. If I now remove, let's say, something, and I change it to be something else, and I run, here we go, I have a semantic error. They expected something, but got something else. That's exactly what we thought would happen. Yeah, the something that's a little bit lacking on this project is the errors aren't the nicest. Sometimes you do get really nice errors from the parser. So for example, the close tag expected left in slash, because it thinks that this is going to keep going for a long time and it's not going to be a closing tag. and the error handling could definitely be improved. But it works really well. If now that I've restored order, all works well. There's a second part of the project that I want to show you, and let me just stash the changes. Presenting parser. If I stash the changes, here you can see I actually have some JavaScript stuff. So this is because I have built this project to run on WASM because I wanted to test it. And I think it would be really useful for something like testing utilities. So we use a lot of JS DOM, Happy DOM, these type of libraries that can query HTML, which is an XML structure. And they're okay, but they're a bit slow. So I think this would be a good opportunity to run, maybe not WASM, because this would most likely run on Node, but the potential is there to run this stuff on websites. So let me show you how that would work. So I have a JavaScript file, really big JavaScript file, which contains this index stuff. I was doing a couple of tests, but let's run the test only once, and let's actually console log the translated JSON so we can see the representation and see how long that took. So I'm using this really big example that I found online. It's a few hundred lines. Yeah, it's a few hundred lines. Let's see. So if I just go on over to localhost, it's a very, very simple website. Obviously, most of the magic, all the magic will happen here on the console. Okay. So we already get hello from WebAssembly. And if I look at source, maybe it's not quite here. File system page. Oh, page here. Here you can see the actual WASM code that's been translated. Maybe Golang isn't the best choice for compiling down to WASM because it needs to obviously compile all the garbage collected stuff, but it still works really well. So let's have a look at the console, press the button, and there you go. It took about 61 milliseconds, which is really not ideal, and it's much faster running on bare metal and not being compiled to WASM. This can be improved by using TinyGo compiler instead of the regular compiler, but yeah, one thing at a time. And there you go. We have perfectly usable JSON that was converted from a really big string of XML. So yeah, this is my first attempt at building a parser. I'm going to go on to some boring things now, so feel free to tune off. We have the Alexa, where we have our regexes, and we slowly and surely tokenize our code. This is then fed into the parser, and this is a recursive descent. I want to say I learned this all at university, and it was a module I was really fascinated with. So I went to Royal Holloway, and I had the privilege of being taught by Elizabeth Scott. She was really good. And yeah, so I followed the exact algorithm for creating a recursive descent parser, which is super simple and was really nice. I just had to adapt it to obviously be run in Golang and stuff. Have good error handling because obviously there's no go-tos in here. And there you go. Each non-terminal has a parse function, and if I just show you the grammar as well, which is on my blog, this is what the grammar actually looks like. We have an element, an open tag, some attributes. So this attribute stuff would be like the name with the equal sign and a string. And then we have write recursion again. The element has an open tag going on to an element suffix. The element suffix is purely to allow for the self-closing tags, which I didn't demonstrate, but they do work. So you can have a self-closing tag, or you can then have the content and the closing tag. This content is where most of the magic for the nested structures happens. You can have data, which is a literal, so it's all content between these two angle brackets. Write recursion again. Instead of data, you could have an element and then write recursion again, and it could be null, right? Otherwise, it would never stop the recursion. Here we have a closing tag, close tag, which is the easiest non-terminal or non-literal. And then we have our literals. This is the stuff that can be caught by Alexa, by the tokenizer. What's missing really is these ones here, because I do parse for them. These the left bracket, the right bracket, the slash right bracket, and the left slash bracket. I do go for them. I just didn't write them down on literals. It seemed like a bit of wasted space. And obviously we have epsilon, which is just null. Yeah, this was quite an interesting learning step for me, because I wasn't sure how much work the parser had to do compared to the lexer. So I was really scared of having complex tokens like data. Data is a really complex token because it needs to know, it just take everything between these two characters, which has effects. So you can't really use these two characters inside of your text. Some of which is in the XML spec, but some parsers do allow it, and mine doesn't. Name, which is also not really a complex, a contiguous string of alphabetical characters, and also numbers, which I forgot to mention, and string, everything inside these. So I was quite apprehensive of doing stuff like this because I didn't want to put too much emphasis on the lexer, but I realized that regex is actually super powerful, and we should take advantage of that, so to make our parser slightly more simple, and it's a good balance to have, and that's actually one of the points that I had here, lexer versus parser, so I think I learned a lot from that. So that's kind of it. There's only one more part really, which is the semantics, and also the JSON translator, which I'll go through, which just uses a stack. It pushes onto a stack, pops off the stack. That's it. Super easy. And obviously if you get a mismatch of elements, it will tell you that there's an error. The JSON translator, I spent quite a bit of time on this to get it really perfect, but it's a recursive function. That's it. It has a base case where it just returns a JSON string value. That's just the plain data. A for loop to go over the nested elements. So because you could have, like, just like in the text, you could have world something. These all belong to hello. That's what the translator is doing. And it also checks for arrays, because at some point you might want to create an array, which is if the map that I'm using has seen this before. And yeah, and it recurses over and over again. And in our main function here, we just take the very top level element, we take its name, we set that as the map, and then we return the object, and then that's it. And after having these structs, I implemented this print function. So all of these are a part of this interface because they implement print, and print is what actually outputs the nice JSON, so that it can be JSON parsed by JavaScript or any other language or anything. So that's kind of it. It's pretty much fully tested. Test coverage is really good. Probably the best tested project I've ever done. Used a lot of snapshot testing as well, which is a really good feature of Jest that I'm quite used to, so that you can do your tests normally, but then also do some snapshot testing to have some visual feedback to see what's actually going on. The best way to show you this would probably be the translator snapshot tests, which is exactly what you expect, a bunch of JSON. So in the translator tests, I would do stuff like this. I would do long checks directly into the structures of the JSON types. And then I would still do a snapshot test just in case, because I want to see what's going on. And a snapshot test would instantly fail if something is different, so you know something is up instantly, even if you wrote the test slightly wrong. So that's it. It's been really fun to learn more about parsers and compilers and going through the whole spec. I hope to do more projects like this. Thank you for watching. Hopefully you made it this far. Hopefully it's not too boring. I'll catch you in the next one. Thank you.